First time reminding us.
All right, with the full committee assembled, I think we'll get underway here. So it's my pleasure to introduce, for those of you who don't know him, which I think is no one in the room, James Jones, who came to us back in the fall of 2011 from San Francisco, where he's been working with a kind of a rapid prototyping and commercialization company called Think to Build. Before, I guess, a couple years before that, he'd been at Dartmouth doing his both undergraduate and master's work in engineering. Then spent a couple of years sailing around the Pacific and decided that wasn't as much fun as being an engineer, and so decided to come back to graduate school. And he's been a great just person to have in the lab for the last couple of years. It's some really nice work on a new engineering system with a really snazzy name, which he'll get into during the talk, and has really just helped to, I think, safe to say, really push forward the bounds of what we can consider doing with environmental infrastructure around marine energy sites. So the structure of the defense, James is going to give a talk that's going to run roughly 3 hours. It's got enough information for it, but he's promised to keep it a little shorter. We'll go into a public Q&A session after that, followed by a closed session with the committee. And at some point, there may be a snake bite, and James is well equipped for both of us over here. James.
Thank you, Brian, for the introduction, and for everyone here for being here today. It's a lot of good friends and family and everyone here. It's great to see you. It's my pleasure to be presenting to you on my dissertation work on advancing marine renewable energy monitoring capabilities through the development of an adaptable monitoring package and the Millennium Falcon ROV. And the primary motivation for this research has been to support the sustainable development of marine renewable energy, whether that be tidal energy, wave energy, or offshore wind. Basically, with any system that's complex and large as this in the water, it poses a lot of engineering challenges, not the least of which is properly assessing the environmental impacts of such systems on their surroundings. When I talk about environmental impacts, really we can think of this as an interaction between stressors, such as the marine energy converters themselves, and anything in their surrounding environment, such as marine mammals. And when these two things interact, there's probably going to be some sort of change that, if we can measure that change, we can classify it either as a negative effect, which would be an impact, or a positive effect, which could be a benefit. And if we can identify these effects early on in the development process of this technology, then we can mitigate against the negative impacts and hopefully support sustainable development. Over the last few years, there have been a couple key workshops that have looked into these environmental effects and the instrumentation that is used to monitor for them. And from those workshops, we were basically able to put together a wish list of monitoring capabilities, which included the potential to do environmental or spatially comprehensive and temporally continuous monitoring, identify marine animals down to the species level, and be able to adapt the instrumentation in the system to evolving monitoring missions, and do all that, or be able to survive in the energetic conditions typical of marine energy sites. And of course, we'd like to do all this at a cost that is reasonable in the industry for this type of work. And to date, there have been several systems like this developed for specific projects around the world, including the three shown here. But all of these systems had fixed cables that basically require the cable to be recovered with the instrumentation platform to do any sort of maintenance on the instruments. And so we set out to develop our own similar platform for the project that was going to go into the water here in Puget Sound about 4 years ago. And we started off by looking at all the instrumentation that we want to put into such a system, including all of these instruments shown here. And basically, we laid them all out in a single body that respected all the spacing and constraints of the different instruments, and centered them around securement assembly that allowed this package to be clamped onto a docking station and has a wet mate connector in the center that can plug it in underwater. And we call this system the Adaptable Monitoring Package, or AMP for short. And here it's shown with all of its shrouds on, mounted to a standalone docking station that's then cabled to shore. And really, this is a first attempt at a plug-and-socket architecture for this type of instrumentation platform, where the docking station is the socket and AMP is the plug. And what this does is it gives us the added benefit of a cabled system to do real-time continuous